Hello everyone, and welcome back to the channel. Today is Friday, March 6th, 2026, and I am super excited to be here with you all today. I am introducing a trending article from the archives today, and I am just a laid-back guy who loves transcribing YouTubers as if I am talking to myself in an empty room. Sometimes I wonder if my microphone is actually a piece of broccoli, but then I remember broccoli does not have a passive port. Oh well. Let us dive right into the tech. The title is ZeSTA Zero-Shot TTS Augmentation with domain condition trained for data-efficient personalized speech synthesis. The call is TET Recursive 3.4202. It is long, right? So let us really get into the weeds of what this paper is talking about. Because the problem they are trying to solve is actually something we interact with all the time. Imagine you want to create a digital version of your own voice, which is what we call personalized text-to-speech or charts for short. You should make the AI sound exactly like you. It needs hours and hours of high-quality recordings of you speaking in a studio. In the real world, most people or companies do not have that kind of time or money, so we end up with what researchers call a low-resource scenario. This means you only have a few minutes of audio from the target speaker, and you have to somehow train an entire neural network to mimic their unique tone and emotion. Now, one way researchers have tried to fix this data shortage is by using something called Zero-Shot TTS. Zero-Shot models are these massive generative AI systems that can listen to a tiny clip of your voice, and then magically generate new speech that sounds somewhat like you saying completely different sentences. So researchers thought, hey, what if we use this Zero-Shot system to generate tons of fake audio of our target speaker, and then mix it with the tiny amount of real audio we actually have? They call this synthetic data augmentation. It sounds like a perfect plan, but the researchers in this paper noticed a massive problem with this approach. You naively mix a huge pile of synthesized speech with a tiny bit of real human speech. The AI model gets confused during the fine-tuning process. Sure, the model becomes much better at pronouncing words clearly, which improves the intelligibility, but it actually loses the unique identity of the original human speaker. It starts to sound more like a generic AI robot, rather than the specific person you wanted to clone. And this is called speaker similarity degradation. To fix this incredibly frustrating issue, the brilliant minds from Maum AI and Humelo proposed a brand new framework called ZeSTA. ZeSTA stands for Zero-Shot Augmentation with Domain Condition Training, and the core idea is surprisingly elegant and simple. Instead of just throwing all the real and fake audio into the training mixer and hoping for the best, ZeSTA attaches a tiny digital sticky note to every single piece of audio. The sticky note is called a domain embedding, and it simply tells the neural network whether the audio is learning from right now is a real human recording or a synthetic zero-shot generation. By doing this, the AI can extract all the helpful lessons about pronunciation and vocabulary from the massive pile of synthetic data, while reserving the specific acoustic characteristics and vocal identity purely from the real human data. On top of this clever domain conditioning trick, they also use a technique called real data oversampling. This means they take the tiny amount of real human audio that they have, and they intentionally repeat it multiple times during the training process. It is like reminding the AI over and over again what the true human actually sounds like, just in case the AI gets too distracted by all the synthetic audio. The beauty of this combined approach is that it does not require changing the underlying architecture of the base model at all, making it incredibly practical and lightweight for developers to use. When we compare ZeSTA to other existing technologies, the differences are night and day. For example, voice conversion is another older method where you try to transform one person's voice into another person's voice. But that usually requires a lot of complex parallel data and is super tedious to set up. Then you have the massive foundational zero-shot models like Verblox or Ideal, which are incredibly powerful, but way too heavy and expensive to run on a normal computer or a smartphone. ZeSTA hits the perfect sweet spot, because it allows you to build a lightweight and highly personalized voice model, using the intelligence of those massive minds without actually having to deploy them in your final product. The researchers proved this by running extensive experiments on two datasets called Librets and an in-house dataset called Ubund. They used objective metrics like the speaker embedding a size similarity to measure how much the voice sounded like the target, and word error rate to measure how clear the speech was. They found that ZeSTA drastically improved the speaker similarity compared to the naive mixing method, but keeping the word error rate impressively low. Now let us talk about how this mind-blowing technology could actually be applied to the real world. Because I can think of at least 3 amazing use cases right off the top of my head. First, let us talk about medical applications. Specifically for patients who are slowly losing their ability to speak due to conditions like Alzheimer's neural disease. These patients often want to bank their voices so they can communicate with their loved ones using a speech device later in life. However, they might only have the energy to record a few minutes of clear speech before their voice gets too tired. Using the ZeSTA framework, medical technologists could take those precious few minutes of real audio, generate hours of synthetic augmentation, and use the domain condition training to build a highly accurate, lightweight digital voice that sounds exactly like the patient. This would give them their true voice back, running efficiently on a small tablet on their wheelchair without needing an internet connection. Second, think about the independent video in development industry. E-game developers usually do not have the budget to hire dozens of professional voice actors for their massive role-playing games. They might only be able to afford an actor for 1 hour in the studio. With ZeSTA, the developer could take that 1 hour of recording, use a public zero-shot model to generate thousands of lines of dialogue for various non-playable characters, and then fine-tune a lightweight e-engines model. Because ZeSTA preserves the actor's unique vocal identity while maintaining perfect intelligibility, the developer can populate their entire fantasy world with rich and personalized voices that run natively within the game without causing massive performance drops. Third, this technology could completely revolutionize localized dubbing for independent content creators and small YouTubers like myself. Imagine, I want to release my videos in Spanish, French, and Japanese to reach a global audience. I obviously do not have the time to sit down and look at thousands of hours of translated audio. I could just provide a tiny 5-minute sample of me speaking, and the localization platform could use ZeSTA to create a highly personalized, multilingual voice clone. The platform could synthetically augment the data to cover all the weird phonetic sounds of foreign languages. That use the domain embedding to ensure the final output still retains my goofy, laid-back personality and specific vocal timbre, but would allow creators to connect with international fans on a deeply personal level, because the translated voice would genuinely sound like them, not a generic translation robot. The researchers even did a Boishi studies to prove why this works so well. They checked what happens if you use synthetic data from a completely different speaker instead of the target speaker. It turns out, if you use mismatched synthetic data, the model completely fails to capture the target speaker identity, proving that the domain conditioning specifically relies on speaker-consistent data to bridge the gap between pronunciation learning and identity preservation. It is just fascinating how giving the AI a tiny bit of context about where its data comes from can completely change the quality of its learning. This paper essentially writes the instruction manual for doing data augmentation the smart way, and it is going to make custom AI voices so much more accessible to everyday people. Thank you guys so much for listening to me ramble about speech synthesis today, and I will catch you in the next transcript.